Chapter 6, Confidence Intervals. So this first section of Chapter 6 is all about a specific when we know our population standard deviation. But first we got to define what a confidence interval is and how we build one. So an interval estimate is an interval or range of values used to estimate a population parameter. So this would be a situation where you cannot actually get the population mean, but we're going to try to use this to estimate what it might be based off of a sample. So in order to create this, you need a point estimate, a level of confidence, and a margin of error. So the first piece of that, a point estimate for the population, would mean in order to estimate our population mean, if we can't possibly get it, is to use the most common one, our sample mean. So in situations like this, we're using our sample mean in order to estimate what would be the population mean. So one of the first questions you might see is just finding the point estimate. And the big thing with point estimate is all it means is find your sample mean. So this example says a researcher is collecting data about a college athletic conference and its student athletes. A random sample of 40 student athletes is selected and their numbers of hours spent on required athletic activities for 1 week are recorded. Find a point estimate for the population mean, mu, the mean number of hours spent on required athletic activities by all student athletes in the conference. So we want to find our point estimate. So X bar means we're going to add up all of these numbers and divide by the sample size. So when you add up all 40 numbers in the chart, you get 842. We're going to divide it by 40 because there are 40 in there. It also tells us in the wording of the problem our sample size. And when you divide that, you get 21.05. Your sample mean, or in this chapter, we call it your point estimate. So once you have a point estimate, the next piece of knowledge you need is a level of confidence, and it is the variable lowercase c. This is the probability that the interval estimate contains the population parameter, assuming that the estimation process is repeated a large number of times. The big thing that's important about this is that it's going to be given to you. This is not something that you have to guess or figure out. It's going to be given, and you need to know how to change from our confidence into a critical value. So critical values are the values that are going to separate your sample statistics that are probable from things that are improbable or unusual. So this is our same normal curve that we saw with normal distribution. And in this case, our critical values are z with the subscript c. So that is these two right here. You've got a negative and a positive one because they're symmetric to each other. So there are two values. You're going to get a positive and a negative version. Now, in this chart on the right shows you the steps that you're going to go through in order to find that. So when the problem gives you a confidence and says something like, we are 90% confident, they're talking about this middle area under the curve. So in this case, the shaded blue area is 90%. Now, in order to find the area under the curve in the tails, we're going to use inverse norm in our calculator. But keep in mind with inverse norm, you always want to use to the left, the area to the left of the spot you're looking for. So we're actually going to put in this area into our inverse norm in order to get our critical values, both the positive and the negative side. So in order to find that piece, there's a little formula over here. It's 1/2 1 minus c. C is the confidence that you were given. So 90% would be 0.9. You plug it in that little formula to get 0.05, which plugs into your inverse norm. And that is where they're getting their critical values from, both the positive and the negative. So again, just with a clean screen, just so you can see that right there, 90% level of confidence. That means there are 90% is in the middle underneath that curve. Now, you could think this out and figure out what's in your tails, because if you know underneath that curve, it adds up to 100%. If you subtract 90% from 100, you get 10%. And because there's two matching tails, we cut that in half. That's where we get the 5%. So the little formula you just saw on the previous slide, 1/2, 1 minus c, is when you plug in 90% as a decimal. So 1/2, 1 minus 0.9, you can see the same process going on here. But this number, 0.05, is perfectly ready to drop directly into inverse norm. So inverse norm of 0.05, again, these are 5% in each one of those tails. Second vars to find inverse norm. And you're going to get from your calculator the negative 1.6449. Keep in mind, your calculator will always give you the negative one, but it's symmetric. So if you got one on the left, you also have one on the right. So really it is positive or negative of that number. And that's the lines. That's what we're trying to find here. These are the z-scores that separate what's probable from what's improbable for these scenarios. So that is your ZC, your critical value. So once you have that critical value, we got to talk about sampling error. It's the difference between your point estimate, which remember is your X bar, and the actual population parameter value, your mu. So we're trying to find how far apart these two things might be. Ideally, we're trying to estimate our population mean, but we only have our sample mean, and that's going to vary. So in order to find this, we use something called the margin of error, also called the maximum error of estimate or error tolerance. So this is your greatest possible distance between your point estimate, X bar, and the value that we are measuring, so our mu. So this is the maximum distance between these two values. So it is a formula. E stands for margin of error. So E equals ZC times your population standard deviation, that's given to you, and then divided by the square root of n. That's your sample size. That is also given to you in your problem. Now, the only two things that we have to check for is that our sample is random, and then it's going to be one of two things. It's either going to say normally distributed in there, or your sample size is bigger than 30. We still need to meet that criteria in order to solve the problems. Now, once you've done that and you've found your margin of error, this is where the confidence interval is written at the end. So you see this setup where our population mean is somewhere in between these two endpoints. But in fact, the way we're going to write it when we submit our homework and on assignments is where we find those two endpoints and write it in interval notation. Interval notation means it's going to be parentheses from one number, comma, to the other number, close the parenthesis. So this is the interval that's most likely going to contain your population mean. This is the interval we're after, especially after we repeat this a large number of times. So real quick, just to recap the steps that you were going through, you are going to check first that you have a population standard deviation, that your sample is random, and it either says normally distributed or a sample size greater than or equal to 30. Then if you are not given your sample mean, you're going to find your sample mean. You are going to find the critical value, which means taking the C that you were given, your confidence, plugging it into the little formula, which then plugs into inverse norm, and that's going to give you ZC. Remember, inverse norm is the backwards of normal CDF. Normal CDF is when you are plugging in Z's to find the area, Inverse norm is when you have the area and you're going backwards to find the z. Then you're going to find your margin of error, and then you're going to create your confidence interval. So let's put all of that together here. So using the data back from example 1, we're going to construct a 95% confidence interval for the mean number of hours spent on required athletic activities by all student athletes in the conference. So I always kind of, when I do this one, split it up into 3 steps: the finding the critical value, finding margin of error, and writing that confidence interval at the end. So I kind of number it that way throughout all of chapter 6, just to kind of keep you on the same reminder of the 3 steps to this. So step 1, you are given your confidence of 95%, which is the same as the decimal, 0.95. So the first thing we need to do is plug it into 1/2, 1 minus c. So 1/2, 1 minus 0.95 gives us 0.025. That is what we are going to plug in for area in inverse norm. The only thing we change in inverse norm is area. The mean should stay set as 0. Standard deviation should remain set at 1. So I'll put that on here just as a reminder. And then when you click enter, this is your critical value. Both the positive and negative of that number, which rounds to 1.9600. And for the purpose of all of our PowerPoints, I am rounding everything to 4 decimals, just in case you're trying to work ahead of me. So 1.9600, that's rounded to 4. This is your critical value. And I'm labeling it as such because sometimes on problems, they want you to find just the critical value or just the margin of error, or maybe go the distance and find all the way to the confidence interval. But this way, by labeling it as we do it, you know what the name of each of these numbers are along this process. So that's your critical value. Step 2 is your margin of error. So that's your E formula. We're going to plug in the positive version of your critical value. You always plug in the positive, times the standard deviation, which was 2.4 for that data set, divided by your sample size, 40. When you multiply, and again, 4 decimals, 0.7438. That is your margin of error. The last step is finding the confidence interval, which is our sample mean minus E and our sample mean plus E. So just as a reminder, our sample mean was 21.05 minus the margin of error we just found. We are going to both add and subtract these to get the interval. And we get 20.3062 and 21.7938. This is the confidence interval. So again, there's 3 steps to each of these. Find that critical value, which leads you into your margin of error, which you wrap up with your confidence interval. So let's try it all again. So this is a new, fresh problem. This one says a college admissions director wishes to estimate the mean age of all students currently enrolled. In a random sample of 20 students, the mean age is found to be 22.9 years. From past studies, the standard deviation is known to be 1.5 years and the population is normally distributed. Construct a 90% confidence interval of the population mean age. So going through here, you have a sample of 20 students, that is your N. You are given your sample mean, 22.9. It says from past studies, the standard deviation is known to be 1.5. That means your population standard deviation, because it said from past studies, that's the clue. It does say normally distributed. It does say random sample. And then here's your given confidence, your C. So we've got all these pieces in here. We're going to move to the next slide just so we have a little bit more space. So the first thing we need to do is find that critical value. So confidence is 90% this time. So 0.9. So we plug it into 1/2, 1 minus C, which gives us 0.05. We plug that into inverse norm as our area. And your calculator will just show you the negative symbol, but it is both positive and negative of that. 1.6449. This is your ZC. That is your critical value. Our next step is to find the margin of error. We plug in always the positive version of our critical value times our population standard deviation over the square root of n. And we get 0.5517. This is our margin of error. And our last step to find our confidence interval is to take our mean, 22.9, minus the E to find the lower end, and then add it to find the upper end of our interval, 22.3483, 23.4517. This is your final answer here, confidence interval. Now, a quick little note about interpreting the results. Oftentimes we are finding the numbers that we don't talk much about the results, but you will start seeing some conclusion sentences coming up where you'll have to write a conclusion sentence of what these numbers mean. So this is a great slide to come back to as a reference point. Keep in mind, your population mean is a fixed number. It's either in that interval or it's not. That number itself is not moving. So it would be incorrect to say that there is a 90% probability that the actual mean is in the interval. Instead, what we say is if a large number of samples are collected and a confidence interval is created for each sample, the 90% of our intervals would contain our population mean. So that seems a little funny. Here's an image of it. Each one of these horizontal segments represents a 90% confidence interval for different samples of the same size. So if you go out and you take a sample, you put together your information, find your confidence interval, then you do it again and again and again. Notice that 9 out of the 10 of them actually cover your population mean. There's just one that just barely misses that mark there. But this is what it means to be 90% confident, is that 9 out of every 10 would contain that population mean. Now, the last thing we need to do is sometimes you have scenarios where you want to work backwards. Instead of finding that confidence interval, you might want to find a minimum sample size that you might need to collect in order to get the results you want to have. So if you were given a confidence level and a margin of error, you can find the minimum sample size needed to estimate the population mu. Now, when you are solving this, if n is not a whole number that comes out, you're going to then round your answer, your n, up to the next whole number. Notice this doesn't say round up or down. It is round up. So if you get an answer like 7.2, you would round that up to an 8. Or if you got an answer like 16.7, you would round that up to the next whole number, 17. So regardless of the decimal value, you should always be going up when you round. Now, if your population standard deviation is unknown, you can still do this with the sample standard deviation as long as you have at least 30 members in your sample. So as long as your sample size ends up being big enough, you're good to go. So let's see what this looks like. The researcher in example 1 wants to estimate the mean number of hours spent on required athletic activities by all student athletes in the conference. How many student athletes must be included in the sample to be 95% confident that the sample mean is within 0.5 hours of the population mean? Now, just as a reminder, we have our confidence, our C. Our population standard deviation from previous was 2.4. So this is coming back from example 1. The other thing we need from this is the margin of error. And that's always going to come after the word within. So within is your clue word, and what comes after it is your E. So in this case, that margin of error, your critical value, and your population standard deviation will all get plugged in to our formula to find the minimum sample size. The one that we need to work a little bit on is that confidence. We need to get from C to ZC. So from our confidence into our critical value. So 0.95, you can plug it into that 1/2 1 minus C. Then once you have that, 0.025, plug it into inverse norm to get our ZC as 1.9600. So when we go to plug this in, we've got our critical value times our population standard deviation divided by our E, and don't forget the square out back. This gives us 88.51. Just keep in mind, if it's asking for minimum sample size, this has to be a whole number answer, no decimals. So we're going to round this up to the number 89.